Thanks for your listening. And here, the title of my subject is Glimepiride, a novel soluble epoxide hydrolase inhibitor, protects against heart failure via increasing epoxycyanotic acids. And I'm Zhao Chengcheng from Chengcheng Hospital. As we all know, heart failure is a rapidly growing public health issue worldwide. And despite the continuous evolution of treatment methods, hospitalization rates and mortality remain high. Therefore, finding new therapeutic targets for heart failure is urgently needed. EETs are important endogenous cardiovascular protective factors that regulate multiple pathways in various cell types, thereby exerting a range of protective effects including improving ventricular remodeling, anti-inflammatory properties, reducing blood pressure, alleviating myocardial ischemia, rapid injury, and decreasing myocardial infarction area. But the soluble epoxide hydrolase, which rapidly metabolism EETs into downstream substance DHET, only retains 20% of the biological activity of EET. So inhibiting SEH is an effective way to stabilize endogenous EET levels and enhance its beneficial effects. So our scientific hypothesis is that inhibiting SEH and upregulating EETs can effectively improve heart failure. And first of all, we detected the concentration of EETs in 632 participants, including 316 patients with heart failure and 316 healthy controls by LCMS. And we found that 8 different metabolites related to AA through the CYP-ET's SEH pathway were quantified, while 4 ratios were measured to assess SEH activity in comparison to healthy controls. The reduced ETs, which markedly increased concentrations of DHETs and DHET and ET ratios in plasma samples from patients with heart failure, was consistent with the observation in the heart from heart failure mass. And then we also detected the expression of SEH in heart failure mass, and we found that both the activity and the expression of SEH in heart failure issue were increased. And we get that SEH might play a crucial role in the occurrence and development of heart failure. Consistently, the expression of SEH was elevated in the heart from TAC-induced heart failure mass. The previous study illustrated that the dynamically changed cell type cross-TAC during pathological cardiac hypertrophy. We reanalyzed the single-cell RNA sequencing data and found the mRNA level of EpxX2 generally increased in cardiomyocytes during cardiac hypertrophy. Inconsistent immunofluorescence analysis showed that SEH was significantly increased in CTNT marked cardiomyocytes from TAC-induced heart failure mass. Although SEH signal was also co-localized with endothelial and fibroblast-specific markers, its expression was unchanged in endothelial and fibroblasts during heart failure. Therefore, considering the role of SEH in cardiomyocytes, can it affect the overall cardiac function? This result suggested that the decreased ETs with less cardiovascular protection might be caused by the increased SEH in heart failure. So, to determine the action of SEH, we generate a myocardial-specific knockout of SEH mass, and we found that cardiomyocytes were the main cell type of SEH expression, which is parallel to the results above. And after knocking out the SEH, the increase of SEH in the heart of mass with heart failure induced by TAC could be reversed. Also, the cardiac function of TAC-induced heart failure mass could be improved. And cardiac hypertrophy and cardiac injury induced by TAC could be improved in magnitude. So we get the first part of conclusion. SEH was upregulated in heart failure and showed significant differences in cardiomyocytes. After myocardial-specific knockout of SEH, the myocardial hypertrophy caused by heart failure could be obviously improved. So, what is the mechanism of upregulation of SEH? To further explore why SEH was upregulated during the stress-caused heart failure, several assays were performed in vitro. Among the three main pathways of neurohormonal alteration under heart failure, only angiotensin II treatment led to the enhanced SEH expression and activity, which was consistent with the results conducted in endothelial cells. And further, the upregulation of SEH expression in angiotensin II treated cells was confirmed by immunofluorescence. Based on the effects in vivo, we hypothesized that SEH played an essential role in angiotensin II-induced cardiac hypertrophy, and the immunofluorescence study of affecting validated that the decreased SEH could elevate angiotensin II-induced cardiac hypertrophy, as well as the cell injury represented by the elevated transcription level of BNP. Meanwhile, the mRNA level of EPHX2 was also increased after angiotensin II treatment. Therefore, the potential transcription factor of EPHX2 was predicted by bioinformatic analysis. Among the top 10, KLF15 was reported as a key transcription factor related to cardiac hypertrophy and cardiac remodeling induced by TAC or angiotensin II. Dual luciferase reporter assays also revealed that KLF15 could enhance the transcription of EPHX2. In addition, chief qPCR of KLF15 was performed in angiotensin II treated AC16 cell, which is explicated that angiotensin II markedly promoted the increment of KLF15 to the predicted binding region of EPHX2. Moreover, overexpression of KLF15 could increase the potential level of SEH, while downregulation of KLF15 largely abolished the angiotensin II-induced SEH. Importantly, the expression of KLF15 was also increased in the hearts from TAC-induced heart failure as compared with sham ones. Collectively, angiotensin II could induce cardiomyocyte hypertrophy by increasing SEH via KLF15, which suggested the potential therapeutic strategy targeting KLF15 SEHX against cardiac hypertrophy and dysfunction. Whether SEH could be a therapeutic target for heart failure and what's the mechanism of its action. Considering that a transcription factor KLF15 could affect multiple genes, targeting KLF15 might bring side effects in clinical use. So we're considering the inhibition of SEH, a much more direct and efficient way, had attracted worldwide attentions recent years, especially in cardiovascular diseases. To seek novel SEH inhibitors as potential drug therapies for heart failure, we screened 13 drugs containing your group, which are common pharmacophores in published SEH inhibitors, such as the commonly used AUDA and TPPU, using an SEH recombination protein to test the inhibitory effect of these compounds. In the first screening, glimepiride inhibited the activity of SEH over 35% at different concentrations and by 54.88% with 10 mmol. Then, based on the structure of glimepiride, we tested the half maximal inhibitory concentration of 5 similar drugs, some SEH and Zhao. In the second screening, glimepiride had the lowest IC50. Meanwhile, those 5 drugs were detected with different concentrations in AC16 cells using CCKH assay. In the screening, 4 compounds with barely toxic were selected for further analysis. Using LCMS, we evaluated the biological inhibition of the DHETs and the EETs in AC16 cells. Among them, only glimepiride significantly decreased the ratio of them, which exhibit a similar effect to that of BODA. However, another 3 compounds showed weaker inhibition of SEH activity. Meanwhile, the protein levels of SEH had no difference between the treatment with glimepiride or not, and glimepiride binded well to the active site of SEH. Together, we found that glimepiride, a third generation of drug with its activity, might also inhibit SEH activity. To confirm the contribution of glimepiride in angiotensin to induce cardiac hypertrophy via inhibiting SEH, we conducted immunofluorescence by staining F-actin. The results show that the enlarged AC16 cell area induced by angiotensin II was attenuated by glimepiride, which could be compromised by 14-15-EZE and EET-specific antagonist. Meanwhile, the elevated transcription level of BNP by angiotensin II activation was rescued by glimepiride, boosted by 14-15-EZE and EET-selective antagonist. Previous studies in our laboratory have shown that CYP2D2 and its metabolites, EET-induced phosphorylation of AKT nucleus shift through AMPK, thereby reversing the occurrence of myocardial hypertrophy. So we detected the expression of them, and we found that glimepiride could inhibit SEH, upregulate EET, and reverse the decrease of phosphorylation of AKT level in angiotensin II-induced cell cardiac hypertrophy through AMPK-AKT pathway. And to further investigate the effects of glimepiride in vivo, we fed TAC-induced high failure mass with glimepiride. LCMS measurements suggested that glimepiride could reduce the ratio of DHET to EETs in plasma. The cardioprotective properties of glimepiride was presented by improvements in EF and FS, as well as other analysis. Additionally, glimepiride effectively attenuated cardiac hypertrophy, as evidenced by a reduction in heart size and HW and TL ratio compared to sham-operated hearts after an 8-week follow-up period. In line with this, the enlargement of the cardiomyocyte area in TAC mass was reversed by glimepiride, as confirmed by HE staining and WGA staining. Furthermore, the MRI level of BNP was also rescued by glimepiride. Then, in vivo experiments further corroborated the cardioprotective and anti-hypertrophic properties of glimepiride as an SEH inhibitor. In summary, stress-induced KLF15 increased SEH transcription in cardiomyocytes, which in turn led to cardiohypertrophy and dysfunction. Interestingly, glimepiride, which was identified as an SEH inhibitor, displayed beneficial functions in heart failure mass, which met provide a strategy in the clinical treatment of heart failure. And thanks for Science Father, thanks for organizing committee. Thanks for the guidance and support of my supervisor, Professor Zhao Wang and Professor Chengcheng. Thank you for the Professor Xiang Ruijiang and his project group from Shanghai Institute of Material Medicine. Thanks for your listening. Thank you.